The goal of this lab was to analyze the motion of a spring mass that swings in an arc while oscillating. And the result that I got, which I'll explain throughout this PowerPoint, was that the predicted motion has a similar motion to the data that we received from the tracker. And I saw that the energy principle was supported by the spring mass system, which I will discuss more when I talk about the results. Some of the physics principles that we used in this lab was Newton's second law, and we also used that Vf equals the initial V plus F net over m times delta T. And we use the energy principle, which is that delta E equals delta K plus delta potential spring force plus the delta potential gravitational force. And we applied that throughout the experiment. I'll talk about that when I talk more about the code and how we applied it in this case. So first what I did was that I used Tracker to analyze the system. And so the spring mass system was originally pointing downwards on the y-axis. The length was calibrated, and on the table, you can see that the x and y positions of the systems were given at different times. So I used this to plot the x and y positions given from the graph so that it could help me really visualize the differences between how they looked based on if the oscillation was in the x or the y, which you can see down below. And then I compared the results that I got from Tracker to what we calculated throughout the code. So as you can see, some of the initial conditions that I had to change was that I changed the ball's mass. I also changed the position functions because the ball started at rest, so V would also be 0. And then it also helped me run the x and y positions from the file with some of these equations. So some of the changes that I made on this part was that I showed that the weight force, I showed the weight force plus the rope force. I set T equal to 1.52 seconds, and then I used that all to calculate K, and the equation for that is 4 pi squared times m over T. So you can see I did the calculations here, and I ended up getting 6.87. The spring force is K of S, mg is K times L minus L naught, and then L naught is L minus mg over K, and I calculated that using the numbers that I was given, and what I found for K, I got 0.127 meters. I also used some of the equations I used was kinetic energy, which is 1/2 mv squared, the gravitational potential energy, which is mgh, and the spring potential energy, which is 1 over s times ks times s squared. And in this case, F gravitational only considers the y component because that is the only component that's actually that is interacting with. So we don't look at the x component in this case. And then for the force of the spring, the S is the length of the stretch and A is the compression. And so that differs, based on if it's greater or less than 0. And F net was both the forces combined. And then we also used Newton's second law to find the updated position and velocity. And so as the position of the spring changed, the stretch and compression changed as well. So the code updated this visual model each time. And at each time interval, the kinetic energy, gravitational potential, and spring potential energy was updated and plotted to kind of show the differences in energy. So the code ended up comparing the x and y positions to compare the predicted versus actual outcomes that we got. And so, one was from Tracker and one was from the code. So we compared the two. And so what I found when we plotted this graph was that the predicted and actual were similar in motion, but not really an exact match, probably due to a variety of errors, including maybe a round-off error, or because it was hard to pick an exact point of mass. So in this case, you can see the blue was the kinetic energy, the red was the spring potential energy, and the green was the gravitational potential energy. And the sum is in yellow, which is 0, which shows that energy was conserved and that the energy principle ended up being satisfied. So for the results, for your model system, is energy principle justified? I just talked about this, but yes, the work done by the surroundings equals a change in energy, which was shown when that yellow line was 0. So since there's nothing in our surroundings because the Earth, spring, and mass make up our system, the changes in energy should be 0, which I just showed on the graph. And then it says, using the data you obtain in Tracker, make 2 separate estimations of oscillation periods, basically by estimating the x and y positions and comparing the two. And so I found that the period of oscillation for x was 1.7 versus the period of oscillation for y, which was 1.52, and the difference was 0.18. And they basically differ because the equation to find both different values. So the y position time period is based on mass and stiffness, while the x position time period is based on gravity and length. So that basically means that it would take much longer to move in the x direction versus the y direction. And the x moves in kind of a pendulum motion in comparison to the y, which is why there was a difference in the two graphs.